This episode is brought to you by the Music for Scientists album. Click the link in the description to learn more. On SciShow, we've talked about all kinds of big, complicated questions like what happened at the start of the universe. But sometimes the questions that are hardest to answer are actually some of the simplest ones. Like, take mountains. Mountains have a profound impact on the rainfall patterns that shape our weather and climate. But how does rain affect mountain ranges? It seems like an easy question, but geologists have been debating the answer for more than a century, and some of their ideas aren't what you'd expect. Like, what if raindrops actually make mountains grow? If it's true, the implications could shape how we view the formation of the biggest features on our planet's surface. And after decades of searching, the final pieces of the puzzle are starting to emerge, thanks to some radiation from space. Oddly enough, the key to this idea is erosion, the process of wind, water, or ice wearing down a mountain by carrying away small pieces of soil and rock. And intuitively, knocking off bits of a mountain ought to make it smaller. And if erosion were the whole story, that would pretty much be the end of it. But that misses the complex effects of plate tectonics. Plate tectonics describes how Earth's crust is broken into moving chunks. But what matters here is what happens when those pieces come together. When two plates collide, their edges can get pushed up, creating a mountain range. And erosion can affect that process, both while it's happening and long after. It all comes down to erosion's ability to remove material from the mountains and thus weight. See, when mountains get lighter, they act differently. For instance, during the slow collision between plates, lighter plates will experience less friction as slabs of rock slide past each other on their journey upwards. And less friction means the tectonic forces have an easier time pushing the mountain upwards, making a taller mountain. Then there's another factor called isostatic equilibrium. That's the idea that the tectonic plates are essentially floating on the mantle, and their height is the balance point between gravity pulling down and buoyancy pushing up. Just like how an empty boat sits higher in the water than a fully loaded one. As mountains are eroded away and become lighter, they can float higher. So erosion can give an extra lift from below by accelerating the tectonic forces already in motion. Now, it's worth acknowledging what might seem like an obvious problem with this. Even if erosion makes a mountain lighter, it seems like wearing away the rock should also make the mountain shorter. And here, the key is that geologists think a lot of this erosion happens not on a mountain's peak, but in river valleys lower down. These are areas of intense erosion, and by cutting into the side of a mountain, they can remove a lot of weight without removing a lot of height. So overall, it seems straightforward. Rain creates rivers, rivers erode mountains, the mountains become lighter and ultimately taller. Except here's the problem. All of this rests on that first idea, that rain drives erosion through rivers. But geologists have had an incredibly tough time proving that. Like, there are a lot of things that provide water for rivers, including rain, underground aquifers, and the seasonal melting of glaciers. So to claim that rain is the primary driver of the erosion that might grow mountains, someone needs to show that changes in rainfall actually correspond to changes in erosion. And isolating those details has proven so difficult to do that it took until 2020 to do this in a tectonically active mountain range. To do it, a team looked at how rain affects rivers cutting into the Earth's tallest mountains, the Himalayas. And to measure the rate of erosion, they relied on something kind of surprising: cosmic rays from space. Cosmic rays are highly energetic particles that come from the sun and beyond. And when they strike rock, they can sometimes interact with the minerals inside to produce a form of the element beryllium called beryllium-10. But this only happens for rocks near the surface, like during or after erosion. So when you look at a sample of eroded rock, the more beryllium-10 atoms you see in it, the longer it's been since it was eroded out of a rock. In the study, researchers used that information to figure out how fast erosion was happening in Himalayan river valleys in Bhutan and Nepal. Next, they built computer simulations of the rivers themselves, including their watersheds. Then they enter rainfall data into their river models to see if they could reproduce erosion rates that match what they observed using beryllium-10. And it worked! Erosion from their modeled rivers does in fact depend on how much rain falls in the area. And somehow, this is only one piece of the puzzle. The next step is to link these findings with a model of the tectonic forces to quantify how strongly this erosion affects the height of a mountain. But if scientists couldn't say with confidence that rain contributes strongly to the erosion effects of rivers, the rest would be kind of a moot point. So score 1 for finding the evidence needed to back up our hypotheses. It's not always the most glamorous part of science, but it's one of the most important for understanding our world. And if you like considering questions like this, you might also really enjoy a new album by Patrick Olson called Music for Scientists. It's a tribute to those who've dedicated their lives to science-driven work and was inspired by the space between human creativity and what Richard Feynman calls the inconceivable nature of nature. If this sounds like something you'd enjoy listening to, you can click the link in the description to start streaming.